The continuous increase in fossil fuel demand and fuel prices, together with the growing accumulation of HDPE, high-density polyethylene, and LDPE, low-density polyethylene plastic waste, has become a major global challenge. The heavy dependence on non-renewable energy resources threatens long-term energy sustainability, while discarded HDPE and LDPE plastic persist into the environment for decades, causing serious land and water pollution. These interconnected issues highlight the urgent need for an innovative and sustainable solution. Therefore, this project proposed the conversion of HDPE and LDPE plastic waste into the pyrolysis oil through the pyrolysis process, transforming plastic waste into a valuable alternative energy resource while reducing environmental pollution and promoting a circular economy.
Yeah. Plasto-Fuel is degradation of biomass by heat in the absence of oxygen, which result in the production of charcoal, liquid and gaseous products. The potential to replace fossil-based solution in the iron and steel industry. Selective sorption of oil using plastic waste is presented from almond shell was co-pyrolyzed with high-density polyethylene HDPE polymer to investigate the synergistic effect on the product yields and composition. The pyrolysis of thermal cracking in an inert atmosphere of waste plastic, particularly polyolefins, arouses great interest for the valorization of this waste, as it allows high yields of fuels and raw materials to be obtained, the benefit of the petrochemical industry.
For objective, to produce pyrolysis oil from a mixture of high-density polyethylene or HDPE and low-density polyethylene or LDPE through the pyrolysis process as a potential alternative fuel source. Second, to investigate the effect of different HDPE and LDPE mixing ratios and the yield and quality of the pyrolysis oil produced. Third, to determine the optimum HDPE and LDPE mixing ratio that maximize pyrolysis oil production while enhancing its fuel properties. Fourth, to evaluate the potential of HDPE and LDPE plastic waste as a high-value feedstock for alternative fuel production, thereby contributing to sustainable plastic waste management and environment pollution reduction.
For the methodology, pyrolysis is the most researched thermochemical technique in the past decade among the few well established methods for treating biomass and biogenic waste in order to produce high quality and yield energy products such as biochar, bio-oil and polyethylene gas. 1. Literature review. Conduct a comprehensive review of previous studies, journal and technical publication related to the pyrolysis of HDPE, high density polyethylene, and LDPE, low density polyethylene. Analyze the optimal operating conditions, including temperature range, operation time, and your oil yield reported in previous research. Identify research gaps and establish the experimental parameters for this study. Number 2, collection and preparation of feedstock. Collect HDPE and LDPE plastic waste from household and commercial sources. Sort the plastic to remove contaminants and unsuitable materials such as PVC and wash, dry and shred the plastic into small uniform pieces approximately 2 or 5 cm to ensure the efficient heat transfer. Number 3, prototype development and pyrolysis system setup. Design and assemble a laboratory scale pyrolysis prototype consisting of airtight reactor, heating chamber, condenser, oil collection vessel, gas outlet system. Ensure the reactor is completely sealed to maintain an oxygen-free environment during thermal decomposition.
Number 4. Experimental procedure. Load the prepared HDPE and LDPE feedstock into the reactor. Heat the reactor to 400 or 500 degrees Celsius under oxygen-free conditions. Maintain the required operating temperature until the plastic decomposes into hydrocarbon vapors. Number 5. Vapor condensation and oil recovery. Pass the hydrocarbon vapors through a condenser to convert them into liquid pyrolysis oil. Collect the condensed oil in a storage container. Recover the remaining non-condensable gases for potential use as a supplementary heat sources. Number 6. Product characterization and data analysis. Record initial mass of plastic feedstock, reaction temperature and processing time, mass and volume of pyrolysis oil, percentage oil yield. Evaluate the physical characteristic of the oil, including color, viscosity and appearance. Compare the experimental findings with published literature to determine the effectiveness of the developed prototype. Number 7. Evaluation and conclusion. Assess the overall efficiency of the pyrolysis process. Evaluate the feasibility of pyrolysis oil and alternative fuel. Analyze the environmental and commercial potential of converting HDPE and LDPE plastic waste into available energy resources.
The most relevant United Nations Sustainable Development Goals SDG are SDG 7, Affordable and Clean Energy. For objective, ensure access to affordable, reliable, sustainable and modern energy for all. Relation to the project, produce pyrolysis oil as an alternative energy source, reduce dependence on conventional fossil fuels, promotes waste to energy technology. Other than that, SDG 12, responsible consumption and production. For objective, ensure sustainable consumption and production patterns. Relation to the project, convert HDPE and LDPE plastic into a valuable resource. Reduce plastic waste sent to landfills. Support the principles of a circular economy by transforming waste into useful products. Lastly, SDG 13, climate action. Objective, take urgent action to combat climate change and its impact. Relation to the project, reduce environmental pollution caused by plastic waste, encourage sustainable waste management practice, support effort to lower environmental impact associated with plastic disposal.
For social impact, it increases public awareness of sustainable plastic waste management, encourage the adoption of innovative waste to fuel technology, and last, inspires future researchers to develop environmentally responsible energy solutions.